Here we go with section 6.6, which are logarithmic equations. And basically, sometimes we just want to keep them in logs and get them looking like each other on both sides of the equal sign, and then setting the arguments or the mantisses equal to each other. Or sometimes we want to change them to the exponential form and go from there. But basically, that's what we're going to be dealing with as we work through these problems today, or in this particular section. So if we look at number 1, we have the common log of x plus 5 has to equal the common log of 5x plus 1. Now this is probably one of the most simple types of problems that we can deal with, in the fact that if we have a logarithm on both sides, then the arguments here have to be equal to each other in order for this to be true. So in essence, this becomes x plus 5 has to equal 5x plus 1. And so we subtract x from both sides and subtract 1 from both sides and divide both sides by 4 so that x equals 1. And it does not take much to plug this in and realize that x equals 1 would be a fine solution here. Example number 2, on the other hand, gets a little bit more complicated. It's still not very difficult here, but it's log base 3 of x plus log base 3 of x minus 24 equals 4. Now, one of the first things that we want to do is to calculate or realize that when we add here, this is actually going to be multiplying this x times the x minus 24. So let's see what we get here when we do that combination. This is log base 3 of x times x minus 24, and that's still going to equal 4 on both sides. So now, in order to get rid of this log base 3, because here's a situation where we don't really want to have the log base 3 anymore, we can realize that, or what we could do is we could take 3 to this power, 3 to the log base 3 of x times x minus 24 equals 3 to the 4th power. And in fact, that's where we're going to go, because realize when we do 3 to the log base 3 of x times x minus 24 equals 3 to the 4th power, realize that since taking it to the power is the exact opposite of the logarithm at that same base, in essence, I mean, mathematically we can't say they eliminate each other, but they do disappear. And so when anytime you have the base 3 taken to the log base 3, whatever is left there is what's going to remain. So we get x times the quantity x minus 24, and 3 to the 4th power is equal to 81. And so we can go from here pretty easily. It becomes a simple algebra problem at this point. X squared minus 24x equals 81. Subtract 81 from both sides so that we can do some factoring. Let's see, I believe this can factor into x minus 27 and x plus 3. I think that's what that factors into. So setting each one of these equal to 0, we get x equals negative 3, or we get x equals 27. And we do want to make sure, does that make sense into the original problem? And if we look, if we try to plug in what is log base 3 of negative 3, This one we have to eliminate due to the fact that it's out of our domain. Remember that the domain of logarithms are 0, or the argument here, this has to be greater than 0. And so if we plug in -3, we have to eliminate that one. But let's see if 27 works. Can we log in 27 there? Yes. And we can plug in 27 there as well, and we still get a positive. So the answer should be x equals 27. That's one thing you do need to make sure, is that after you find the values, you need to make sure that they are still within the domain. Otherwise, it's not quite a good picture. Okay, number 3 is log base 4 of x plus 4 equals 4 plus log base 4 of x plus 3. Now, to me, this just screams out that I can get so many things going on here. One of the things, I can change this 4 to actually to become log base 4 of 16, or correction, log base 4 of 256 if I really wanted to do that. And perhaps that's what needs to be done. Or I can put all the logarithms on one side and then deal with it much like I did in number 2. So let's try that one. Let's subtract this log base 4 of x plus 3. And so I get log base 4 of x plus 4 minus log base 4 of x plus 3 equal to 4. And I know, since I'm subtracting, that can be combined into one quotient, x plus 4 over x plus 3, and that's still going to equal the 4. And then if I take to the fourth power, 4 to this power equals 4 to this power, then I get rid of the logarithms. So it's x plus 4 over x plus 3, and as I said before, 4 to the fourth power is 256. So then it's just a matter of solving from here. Multiply both sides by x plus 3, and I get x plus 4 equals 256x plus 7. Let's see. Did I make a mistake somewhere? No. Let's see, plus, okay, 256 times 3 is 768. Okay, so what I can do is I can subtract x from both sides. So we get 255x plus 768 equal to 4. I can subtract 768 from both sides. So 255x equals negative 764, and then divide both sides by 255, and I think nothing will simplify here. Negative 764 over 255. Now we do want to verify that, does this indeed work as far as arguments? We have to make sure it still fits within the domain. Okay, negative 764 255ths is less than negative 3, or it's slightly bigger than negative 3. So about negative 3 plus 4, yeah, that's still positive, and negative slightly bigger than negative 3. Is that what I wanted? 510, 560. It's slightly greater than negative 3, so this would be negative 2.9 or something like that. Plus 1, yeah, it's still positive, and so that does work. And so the final answer is negative 764 255ths. Continuing with a little bit of a different type of problem, we need to solve for f of x equals g of x. Well, that's not too difficult. rather than writing the original problem, I'm just going to write what we need to do. We need to let f of x equal g of x. Now this one's pretty simple. Log base 4 of this equals log base 4 of this. In order for this to be equal, both of the arguments have to be equal to each other. So we get x plus 3 equals 2x minus 9, and it's simple algebra from this point. Subtract x from both sides, and add 9 to both sides, and x equals 12. As a quick check, that would be positive, that would be positive, so both of the domain has been maintained, it hasn't been violated. Example number 5. Number 5, we're talking about pH, and we know that pH is equal to the negative log of x according to the problem. And x represents the concentration of the hydrogen ion in moles per liter. Now, we are asked to find the hydrogen ion concentration if pH is equal to 10. So this is simply a matter of solving this problem. Plug in 10 in for the pH, and then start solving from there. Divide both sides by -1, so that the logarithm of x is equal to -10. And take 10 to both powers here, and so it'll become 10 to the -10th power equals 10 to the log of x. Now the reason I chose 10 is because anytime we don't have a base here, we assume, or no, we actually have to say that that is the common logarithm, which means base 10. And anytime we have 10 to the, or a base to the log of the same base, those in essence disappear. So we get x equals 10 to the -10th power, which will equal 1 over 10 to the 10th power. Very minute amount, but it's still there just the same. Okay. Now 6 and 7 we actually get into exponential equations, and exponential equations can be solved pretty simply. Basically get the bases to be equal to one another, if you can. Now we will see several examples coming up that sometimes it's just impossible to do. But if we go back to, say, number 6, 4 raised to the 5 minus 3x power is equal to 1 over 256. Now hopefully it's pretty obvious that we see 256 is a power of 4. Maybe it's not quite so easy, but it shouldn't take too much guessing and checking to see if that is indeed the case, and that's what it is. 1 over 256 is equal to 4 to the -4th power. And as soon as we get the bases exactly the same, then we know the exponents have to be the same. So we get 5 minus 3x has to equal -4, and then we go from there. Subtract 5 from both sides, and then divide both sides by -3, and x equals 3. Example number 7 is 9 raised to the 7x plus 3 equals 27. Now the problem is, 27 is not a power of 9. However, I should also look at this and say, hey, 9 is a power of 3, so is 27. So that means I should be able to change everything into terms of base 3. And so I know 9 is 3 squared. So all that does is change this a little bit. I'm going to take 3 squared raised to the 7x plus 3 power. And this is going to become 3 to the 3rd power, because 3 to the 3rd power is 27. So then all I have to do is, since the bases are the same, I just have to set the exponents to be the same. distributing here, 14x plus 6 equals 3, subtract 3, and divide both sides by 14. X equals negative 3/14. And that is the answer for number 7. Realize with graphing calculators, or actually a scientific calculator would do this, just simply punch in 9 raised to the 7 times negative 3/14 plus 3, and you better come up with 27. And it's not difficult to check these particular problems. Okay, now the rest of the problems are potentially going to require a calculator. And so if you don't have your calculator, you will want to pause and to get those. But realize that we have several problems that can go along with this, such as number 8, 1/3 to the x power equals 16. Now, in order to solve for x, what we're going to have to do, since this is a base, we're going to have to take the log. I mean, this says 1/3 raised to the x power. So to get rid of this 1/3 to the power, what we're going to have to do is we're going to have to take the log base 1/3 of 1/3 to the x power. But in order to keep things equal, we need to take log base 1/3 of 16 on this side. Now, we have to remember a couple of things, because first of all, log base 1/3 of 1/3 to the x, in essence, these disappear because we're doing the exact opposite. We're taking the logarithm of the base to the exponent. So several different things that are going on here, but in essence what happens, we get x equals log base 1/3 of 16. And we need to remember that from the previous section, that would be the log of 16 over the log of 1/3. So very quickly, and I'm not going to do this for everything, but I will go into the calculator to do that calculation. But realize from now on, if you require to do the calculator, do some practice, get some practice with it. And here is what we're going to do with this problem. We need to find, I'm going to clear out stuff, I need the logarithm of 16, close that out, divided by the logarithm of 1/3. So 1 divided by 3, close that out, and hit enter. And my answer, rounding to 2 decimal places, since that's what it asks, negative 2.52. So the answer here would be negative 2.52. Now as we look at number 9, we have e raised to the x plus 2 power equals 5. Now to get rid of e to a power, what we have to do is we have to take the natural log of both sides. So if we take the natural log of e to the x plus 2 equaling the natural log of 5, then the natural log and the e somewhat cancel each other out. I mean, they don't cancel, but they are doing the inverse of each other. And so we get x plus 2 equals the natural log of 5, and just subtract 2 from both sides, so that x equals the natural log of 5 minus 2. Now we are asked to round this to 2 decimal places, and so what I would do is I'd go to my calculator, natural log of 5, and then just minus 2, making sure that I close out the parentheses here at natural log after the 5, and then minus 2 gives me negative 0.39. One of the places where exponential functions and logarithms can be used is in compounded interest. And we have a formula which is given in problem number 10. A equals P times 1 plus R over N raised to the NT power. where A just represents the final amount that we're going to end up with. P is the principal, how much did we originally put in. R is the tax rate in a decimal. N represents how many times we compound it per year. So quarterly is 4 times, monthly is 12, so on and so forth. And T would represent the number of years. So in this particular problem, we're asking how long will it take a $3,200 investment. So $3,200 goes right there, to double. Well, in order to get double, the amount would have to end up being $6,400. So we know the ending amount has to be $6,400 in order for it to be doubled. If it is invested at 8%, so that's 0.08, and compounded quarterly means there are 4 numbers there. And so notice N shows up both here and here, so 4 times a year, quarterly. So 4 goes there, 4 goes there, and we need to find to the nearest tenth of a year. Well, we need to do some simplifying here first. I'm going to take 3,200 or 6,400, take both sides and divide by 3,200, and we get a 2. Now that 2 should really mean something to you, and if you think about it, it shouldn't take too long to realize we're trying to double our money. That's where that 2 comes from. Now what we have at this point is we can do a simplification here. This isn't too difficult to do. 1 plus 0.08 over 4 ends up being 1.02 raised to the 4t power. So to get rid of this 1.02 raised to the 4t power, we're actually going to have to take the log base 1.02 of both sides. And when we take the log base 1.02 of this becomes 4t because the base then disappears. So to solve for t would become log base 1.02 of 2 all over 4 when we just simply divide both sides by 4. And what we need to realize is that, okay, we've got quite a mess here because log base 1.02 of 2 we have to use the logarithm function, or the change of base, I'm sorry. So that would be the log of 2 over log of 1.02 over 4. Because we don't need to do anything with this, we just need to eventually divide by 2. And when we get all of this said and done and round, and we're told round to the nearest tenth of a year, we end up with 8.8 years. That's what t equals, 8.8. And that's what should happen here when you take log of 2 divided by log of 1.02 divided by 4. And then the last two say use a graphing calculator to solve the equation and round your answer to 2 decimal places. Now, using the graphing calculator is certainly doable, and I will show you how to do it. But honestly, being algebraic here is just a little bit easier, but you know, we're asked to use the graphing calculator, so that's what we will do in each instance. So whenever we are asked when do 2 things equal, what we have to do is to actually create 2 different graphs and see where they intersect with each other. Now this is something a little bit new. We haven't done this yet, so here we go. First thing we're going to do, I'm going to clear out everything that I've already got there, and then go to the y equals and clear out everything I've got there. Now, just like always, I want to start with the window of negative 10, 10, and 1, and negative 10, 10, and 1. So that I get a fairly good starting window, I guess. Now, in number 11, I need to find e to the x minus or equals a negative x. So in my first graph, I'm going to say e to the x. Well, if you look, the second shift, or the second button on natural log is e to the x. So I'm going to do second e to the x. And it gives you the option, I need to put an x in there. And so I've got e to the x as what I need on my first graph. I'm going to hit enter so that I get down to the second graph, and I need to compare that to a negative x. And then I need to actually graph those two things and actually watch what's going on. Okay, there's my e to the x, and here is my negative x. And so what I need to do is I need to find the intersection point right there. The problem is, this is really confused with the axes. So I'm going to go change my window, and I'm going to change my minimum from -2 and 2. And maybe that will help make it a little more clear. Well, it's a little bit better. And I'm still having a little bit of problems, so I'm going to also change the y. Let's change the y so that it becomes, let's see, my y min, let's make it at -1, and my y max be 2. And try and graph that. And let's see, what do we get? Oh, we certainly see an intersection point there. So now it's time to actually calculate that intersection. So let's go to second, calculate, and notice it says intersect. Intersect number 5, option number 5. So it asks for the first curve. Now this is a little bit different. The first curve is e to the x. If you look carefully up here, it's really hard to see on this, I understand, but this is the first curve, so I'm going to hit enter. Then the second curve is the negative x. That's exactly what I want. Well, now if you only have 2 curves, it will automatically choose those. Then hit enter, and then guess what? It asks for a guess. But for exactly the same reason, there's really no need to do it. It will actually calculate generally what is the closest spot. And if we look there, we are wondering what is the x value. The y value we really couldn't care less. It's the x value that is important. Where are the x's equal to each other? And that is at -0.57, because we are told to round to 2 decimal places. So if you round that, you get -0.57. And finally, number 12 will be pretty much the same thing. We just have to put in 2 different equations. So let's go here. Let's start with our window, our default window, -10, 10, 1. And realize we may have to change it so that we can actually see something. Okay, my first graph, I'm going to clear that out, and I'm going to clear out my second graph also, because I have a whole brand new problem. So my first graph, I'm now going to let be e to the 3x power. So I need second natural log, so I get e to the power, and then that will be to the 3x power, so I'm going to put 3x. Now as far as my second one, I'm going to put in x plus 2. So x plus 2, and then graph it and see, is it going to be so confusing that I won't be able to see much? Okay, I can see that it happens up here, maybe about 1, 4, maybe. So I'm going to change my window just a little bit so I can play around with it. I think it's 1, 4, so I'll start at -1 and go to 3 just to make sure. And my y, I'll make it at 0 and go up to 6 because that's what I think it is. Now, I get that graph, and there's the other one. Ah, now I do certainly see the interception way over here. And so we can get an interception here, but we also have to be careful because what's going to happen way over here? There's going to be an interception over here as well. See, if this line continues and this line continues, we will intercept there. So I'll deal with that a little bit later, but for right now, let's just go in here and calculate this interception. So we do calculate and intercept there. First curve, I want to be e to the 3x power as shown. And my second curve, I want to be x plus 2. And I'm going to actually get a guess here, because if I don't guess, then I might end up with something entirely different. So I'm going to guess more or less there, hit enter, and then it tells me my answer is 0.27 when I round that to 2 decimal places. But then I also need to deal with the intercept that's going to occur way over here at the left. So I need to change my window a little bit. I was a little bit presumptuous there. Let's take my x-min back to -10. And when I graph that, notice there's my e to the x, but it is actually along there, and it's also going to show up right here. So that's the intersection that I'm looking for here. So it's more like, it looks like -2, 0. So let's change my window so that that will play out. Change this to a -4 and this to a -1 and see what we get. Do I see an intersection? Well, I don't really see the e to the x because my y values aren't quite right, but realize I can do the calculation and find the intersect. So option number 5, my first curve is e to the 3x, that's okay. My second curve is my x plus 2, and I'm actually going to give a guess. I'm going to guess notice the guess is saying -2 point something. That's fairly close, so I'm going to hit it, and it says -1.997. Well, that's going to round to -2. So, as a result of this, that means the answers would be at x equals -2 or x equals 0.27.